Hello everyone, I am Yugal Bindari, PhD student at University of New England. I would like to welcome you all on my presentation. The title of my talk today is Molecular Detection of Eimeria species and Clostridium perfringens in poultry dust and pool etc. of commercial boiler chicken flocks differing in productive performance. Introduction. Necrotic enteritis and coccidiosis are economically detrimental enteric diseases that are usually associated. Coccidiosis is usually caused by 5 species of Eimeria, whereas Clostridium perfringens type A carrying NATB gene is the most virulent strains capable of causing necrotic enteritis. Monitoring of both diseases on commercial flock is usually based on gut gross pathology, which is subjective, requires skilled personnel, and has no predictive value. So in our study, we evaluated the usefulness of population level samples such as dust and pool etc. with an aim to answer 3 research questions. Can population level samples such as dust and etc. be used to monitor Clostridium perfringens, NATB, and Eimeria species in commercial boiler farms? Can dust be used as an alternative to etc. samples to detect Clostridium perfringens, NATB, and Eimeria species genome copies in commercial boiler farms? Can high and low performing farms be differentiated based on the genome copies load of Clostridium perfringens, NATB, and Eimeria species in dust and pool etc.? Methods. Study was conducted in 16 flocks of 8 commercial boiler farms in a 2x2x5 factorial arrangements with 2 companies, company A and B, 2 farm productive performance, high and low performing farms, and 5 sampling times, 7, 14, 21, 28, and 35 days. Samples for this study were collected by the farm staff of 2 Australian integrator companies. Each company select 2 high and 2 low performing farms. So in total, there were 8 farms. Each farms had 2 flocks. So total number of flocks were 16 from where the samples were collected. You can see here, etc. were collected from the floor. 4 pool etc. were collected from each poultry house. Similarly, dust samples were collected by using dust collection jar. 2 dust collection jars were suspended at 1.5 meter height above the ground in each poultry house. So 2 dust samples were collected from each poultry house. Pool etc. and dust samples were collected at day 7, 14, 21, 28, and 35 days. DNA extraction of the samples were carried out using QAM fast DNA still kit with modification. Data analysis. Repeat measures ANOVA was performed to determine overall load of the pathogens by fitting companies, farm performance, chickenage, and the interaction as fixed effect, and farm nested within company as a random effect. General linear model was performed to determine the shedding profile of the pathogens in each farms across different ages of the chicken. Interclass correlation coefficient was performed to determine the level of genome copy agreement between dust and etc. in each pathogens. All the data analysis were done in GMP14. Results. Detection profile of Eimeria ossergulina genome copies. Here A1 to A4 refers to company A farms and B1 to B4 refers to company B farms. Solid lines in the figure denotes high performing farms and dashed line in the figure denotes low performing farms. In etc., all farms were positive for Eimeria ossergulina. Eimeria ossergulina genome copies load peaked at days 21 and 28 and decreased at day 35. In dust also, all farms were positive for Eimeria ossergulina. Eimeria ossergulina genome copies load peaked at days 21 and 28, whereas there is no further decrease at the last measurement. Intraclass correlation showed excellent agreement between dust and etc. genome copies in case of Eimeria ossergulina. Detection profile of Eimeria maxima genome copies. In etc., all farms were positive for Eimeria maxima. In company A farms, Eimeria maxima genome copies load peaked at day 21 or 28 days and then decreased for farms A1 and A4. Whereas in case of company B farms, Eimeria maxima genome copies load peaked at day 35. Similarly, in dust, all farms were positive for Eimeria maxima. In company A farms, Eimeria maxima genome copy load peaked at day 28, whereas in company B farms, genome copies load peaked at day 28 or 35. Intra-class correlations showed excellent agreement between dust and etc. genome copies in case of Eimeria maxima. Detection profile of Clostridium perfringens genome copies. Clostridium perfringens genome copies in etc. were detected at day 7 in most of the farms and then declined afterwards, except farm B2, in which Clostridium perfringens genome copies load peaked at day 21 and remain elevated afterwards. In dust, all farms were positive for Clostridium perfringens. Clostridium perfringens genome copy load in company A farms peaked at day 14, whereas in company B farms, Clostridium perfringens genome copy load peaked between days 7 and 21. You can see here detection profile of Clostridium perfringens GC in etc. and detection profile of Clostridium perfringens GC in dust were completely different. And interclass correlation also showed that there is no agreement between dust and etc. genome copies in case of Clostridium perfringens. Detection profile of NATB. In our study, only one high-performing farms were positive for NATB. In both dust and etc., NATB genome copies load peaked at day 21 and remain elevated afterwards. Intra-class correlations showed excellent agreement between dust and etc. genome copies in case of NATB. In our study, we found that all farms were positive for Eimeria osserbulina, Eimeria maxima, and Clostridium perfringens, whereas Eimeria tenella and Eimeria necatrix were not detected in any farms. And only one low-performing farms from company A was positive for Eimeria bruneti in case of etc. Overall, there was no difference in genome copies load between high and low-performing farms. This is, you can see, this is the figure of dust and this is the figure of etc. So this is high and low-performing farms. So you can see here, there is no difference in genome copy load between high and low performing farms in case of Eimeria osserbulina, Eimeria maxima, and Clostridium perfringens. Similar results were seen in etc. Overall, Eimeria osserbulina, Eimeria maxima, and Clostridium perfringens genome copy load were similar between high and low performing farms. So this suggests that other factors were associated with performance loss in this study, but not the load of Eimeria species, Clostridium perfringens, and NATB. Usually in case of Eimeria oocyst count above 50,000 per gram of pool, etc. is associated with performance loss. However, in our study, neither of our flocks had the average GC load above 50,000, which indicates that genome copy load of Eimeria in our study is not associated with performance loss. Conclusion. From the results, we can conclude that dust and pool, etc. could be used to detect Clostridium perfringens, NATB, and Eimeria species in commercial broiler farms. Dust can be used as a proxy for etc. samples to determine Eimeria species and NATB genome copies, but not for Clostridium perfringens. High and low performing farms had overall similar genome copies level of Eimeria osserbulina, Eimeria maxima, and Clostridium perfringens. It may be due to low to moderate genome copies load of the pathogens detected in the studied farms. Acknowledgement. We are thankful to AgriFuture Australia for funding this project. We are also thankful to Daniel Smith for providing technical assistance during laboratory analysis. Similarly, we are also thankful to farmers and veterinarians who participated in this study. Thank you.